Good evening, everyone. It is our April Speakers Night for 2023. April already, if you can believe it. Welcome to Rask Toronto Centre. We are online tonight, and I'm Dr. Elena Hyde, the second Vice President of Rask Toronto Centre, and this is our Speakers Night presentation. This is one of two types of gatherings that we have online these days, not at the Ontario Science Centre due to the pandemic. Our President Tom Luton will be talking about our various different kinds of programs later on this evening, but first we have a very special event to kick off. I would like to just start off by acknowledging that the Royal Astronomical Society of Canada Toronto Centre meets on the traditional territories of many Indigenous nations, including the Haudenosaunee, the Confederacy, the Huron-Wendat, the Mississaugas of Credit First Nation, and other Anishinaabe peoples. These lands are part of the Dish with One Spoon Treaty and are now home to many diverse First Nations, Inuit, Métis, and Indigenous peoples from across Turtle Island. As we engage in astronomy here together, we respect, learn from, and honor the deep relationship between Indigenous peoples, the sky, and Earth. Now, on to our special event of the evening, our fantastic speaker, Dr. Hayley Sapers. We're very lucky to have her here tonight. She got her Ph.D. in Canada, actually, as a Vanier scholar, I hope I'm saying that right, in planetary sciences at Western University in Canada, looking at all kinds of fun impact craters, actually. She did postdoctoral work at UBC, McGill, Caltech, and JPL, I believe, so very wide spread of different places. And Dr. Sapers was a Human Frontier in Science Program postdoctoral fellow, who was actually working jointly between the University of Southern California, the California Institute of Technology, and NASA JPL, or Jet Propulsion Laboratory. And she got to work with the Mars 2020 SHERLOC team, which was working with Perseverance Rover on, of course, Mars. How cool is that? Dr. Sapers is currently an adjunct professor and research associate in planetary exploration and astrobiology at the Center for Research in Earth and Space Sciences at York University. She works with all kinds of folks over there doing amazing Mars stuff that she is going to tell us all about today, I believe. So I won't spoil too much of her talk, but I will say that if you're in Ontario tonight and happen to have clear skies and start to get very inspired in about 20 minutes or so, please note that the planet Mars is actually currently visible going down in the west just above a very bright Venus at about magnitude 1.22 or so. And without any further ado, Dr. Sapers, please take us up, up, and away to the red planet.
Thank you very much for that introduction and for the invitation to speak here tonight. It's wonderful to be able to speak here to the Rask Toronto Centre group. So I'm going to talk a little bit about what it means to search for life. How do we do that when we don't really have a good grasp of what life is? And what can we learn about life in the deep subsurface of the Earth and apply that to searching for life on Mars? So intraterrestrial to extraterrestrial, deep subsurface microbial communities, and searching for life on Mars. I'd like you to take a moment and maybe close your eyes, get a little bit comfortable, and imagine that you're in a concert hall. And you're sitting in one of the front rows, right in front of the orchestra, and the conductor is poised. You're ready to hear, you're waiting to hear the very first notes of a beautiful symphony. The instruments are raised, all the bows are raised, and the conductor is just about to lower their baton. At that very first single smallest fraction of a sound, you'll probably interpret that as music. And in the context of this concert hall, you'd be correct. However, if you were out on the street and you heard that very same single smallest fraction of a sound, your brain would interpret it as noise. And you'd also be correct. So how can we take this very same signal, this very same sound that we hear, and come up with two completely different interpretations, depending on the context in which we hear it, and both of them be correct? This is a little bit for how it is searching for life on another planet. We can have a signal or a biosignature, something that life has left behind. And if we're in a place that is habitable, where we might expect life to be possible, maybe this is a sign of life. However, if we find such a signal on the moon, which as far as we know is inhospitable to life as we know it, then this is just an abiotic formation, or maybe a mineral grain, or something that doesn't have to do with life. So this context, this idea of habitability is really, really important. And so is this idea of noise. When we're out on the street and we're looking for that very faint signal, that very faint, very first sound of music, it needs to be a lot louder. It needs to be a lot clearer for us to hear and interpret with all of the noise going on. So I want you to think about this idea of music a little bit more. And I think everybody here probably has some idea of what music means to them. And I think anybody with children, that's been around children, can probably hear this without me playing it. So in Baby Shark, if you play music, maybe you're familiar with this score and you'd recognize it as music, even if you're not familiar with this particular song. Now, if you're familiar with a different type of instrument, maybe this is more familiar to you. So guitar chords or charts. Now, what if you played the koto, a string Japanese instrument? This is traditional koto music. So now the information that we have as listeners or processors of this signal also works into that same idea of context about whether or not we'd interpret that sound as music. If you've never played the koto or never seen koto music, that last figure you probably wouldn't recognize as music. And if you've never seen sheet music and you're not a musician, you might not be able to recognize that song by looking at the sheet music. So this idea of music is very similar to this idea of what is life. You know, we have different types of microbes that might leave different types of signals. We have different types of life as well. And the life we have here on Earth might not be representative of life on another planet. So how can we take what we know, what we're familiar with, and apply that in a situation which might give us something that's completely unfamiliar? Somewhere in between silence and sound lies music. So I'm going to play a piece of music right now, and I want you to just listen to it for a couple moments. And that wasn't a technical glitch. So that piece that I just played is actually a file I have on my computer, and it's John Cage, 533. So I don't know how many people are familiar with that piece, but it's a piece of music purchased by John Cage, performed by John Cage. It's 433, which is 4 minutes and 33 minutes of silence. It's an avant-garde piece, and the idea here is that the music is actually the silence between the notes. And when we think about what makes up music, if we didn't have the silence between the notes, we wouldn't have music. And the music is the sounds the audience makes, the discomfort we might feel when we're expecting something and we don't actually hear what we're expecting. All of that is wrapped up in this concept and this idea of music. And this gets more into that idea of what is minimal life? What is the very smallest component of a biological system before we can actually recognize it as biological? So let's talk about something that's a little bit more familiar. So I'm going to play actually audible music now, and I want you to think about at what point would you consider this to be music? So I'm sure by the last or that third soundtrack, most people probably even recognize the piece of music or even the composer. But the very first one, it almost just sounded like a computer noise or a glitch. And so somewhere in this continuum of silence and sound lies this concept or idea of music, where there's a signal that we can take in and process and understand as music. It might be in sound, it might be an idea, it might be a musical score, it might be a picture of an instrument. And it takes all of those different pieces put together to come up with this concept of music. Similarly, somewhere between non-living and obviously alive is a minimal system of life. And so life doesn't necessarily need to be waving at us. It doesn't need to be talking or walking or intelligent life or a fossil. It could be very simply a set of amino acids or proteins or a single molecule that's so complex we wouldn't expect it to be there by chance. And this very quickly becomes a very philosophical conversation about what constitutes life. How do we go from prebiotic to biotic? And where in that transition can we actually start to detect life? So if we have a planet like Mars that essentially froze and isn't habitable on the surface anymore, we think that the surface of Mars was habitable at some point in the past. Now, was it habitable long enough for that transition to occur between prebiotic and biotic? And if that transition did occur, would we be able to recognize it? And so we have to remember this when we are looking for life on other planets. Earth is our concert hall. We expect life. We know what to expect. But when we step beyond this concert hall, we must be careful not to miss the noise. But we also need to make sure that we're searching in the right place to hear the music at all. So on Earth, life is largely on the surface that we can see. When we think about life, we think about Earth's superficial biosphere. And so this is just a map put out by the California Academy of Science that shows photosynthesis. So this is going to be plants on the ground that photosynthesize and algae in the oceans that photosynthesize. So we can see this have a very obvious signature for life on the surface of Earth. Now, when we think about life on Earth as a whole, this is probably what comes to mind. So we think about lush tropical rainforests, all of this, charismatic megafauna. We have beautiful trees, and we have pandas, and we have horses, and we have dogs, and we have cats. And if I asked you where the majority of life is, you'd probably think it was on the surface. And if we were talking about biomass, the totality of all life, this view is correct. Over 80%, so between 80 and 90% of all life on Earth is marine and terrestrial, and just over 10% is in the deep subsurface. But what if we were to consider life by the numbers? So what if we were to consider microbial life by the numbers? How would this ratio change? We think about, we have billions of microbes just inside humans. There's billions of microbes in a teaspoon of seawater or in a gram of dirt on the surface. But recently, on Earth today, with a perfectly habitable surface, even with the evolution of photosynthesis allowing for all of that life on the surface, over 70% of all bacteria and archaea are in the subsurface, at least 8 meters below our feet. So if we were looking for microbial life on Earth, this is our concert hall. The deep subsurface corresponds to about 2 to 2.3 billion cubic kilometers of habitable environment. That's almost twice the volume of all of Earth's oceans. With a carbon mass of about 15 to 23 billion tons. The continental subsurface goes down to about 5 kilometers, we found life, and the record in marine waters is about 10.5 kilometers from the ocean surface. Now, life in the deep subsurface has an energy limitation problem. It's not getting energy from the sun, and we'll talk about that a little bit later. So this life grows very, very slowly with biomass generation times up to hundreds of years. So if we have very, very slow growing life, and life isn't really doing life things very quickly, it makes it very, very difficult to detect. Now, the subsurface of Mars is thought to be the largest and longest lived habitable environment beyond Earth. So if we're looking to find signs of life beyond Earth, our closest concert hall is going to be the subsurface of Mars. So we have to understand life in the Earth's subsurface a little bit better, how to detect it, what it's doing, how fast it's growing, and what types of biosignatures it leaves behind in order to start searching for life on Mars. So I want to show this one particular microbe. Over the past decade, we've learned that over 70% of all bacteria and archaea live in the deep subsurface, at least 8 meters below our feet, and they live there completely independent of energy from the sun. So they use alternate energy sources. And so this microbe is actually a microbe from a hypersaline cold spring. So this is a spring in the high Canadian Arctic that's over 20% salinity. So it's very, very, very salty water. And because it's so salty, it depresses the freezing point. So the water temperature is actually about -4 or 5. So we have this microbe that's growing in sub-zero hypersaline temperatures. And what it's growing on here is actually an impact glass. So this is an impact glass from an impact crater in Germany that I sterilized and then decided to see if a microbe could actually colonize it in a Mars analog environment. So the subsurface of Mars is thought to have these hypersaline, very cold brines. And so the high Arctic is a great place to try to understand how these microbes might grow. You can see this microbe is actually kind of wired into the rock. And that's because it's getting its energy by transferring electrons to and from this rock. So we breathe oxygen, we're oxidizers. And so in order to get energy, we dump electrons onto oxygen. This microbe is dumping its electrons onto other types of inorganic compounds. So it's breathing rock the same way that we're breathing oxygen. Now, this type of metabolism is probably the most likely metabolism to exist on other planets, especially on Mars, because the surface of Mars isn't habitable today. Microbes can't exist on the surface. So they've got to exist in the subsurface or in brines. And if they're not existing on the surface, they're not going to be using photosynthesis as an energy source. So they're going to be using these alternate energy sources. Now, when we think about life detection missions sent to Mars, really the first and the only truly life detection mission were the Viking missions. And I just want to put the context of the Viking missions into our understanding of the diversity of microbial metabolisms on Earth. And I'm going to start with this cartoon. I love this cartoon because here you have a hydrothermal vent talking to a bunch of tube worms on a hydrothermal vent. And so these tube they're mulling about whether there could ever be life at the surface. And they're postulating, no, there could never be life on the surface because there's no hydrothermal vents up there. You know, what could they possibly use for energy? And this very conversation happened on Earth's surface between scientists in the 70s, in 1977, when the first deep ocean cruise went off that discovered hydrothermal vents. So on that cruise, there was a cruise in 1977 that went out, and it was the first cruise to discover hydrothermal vents off the coast of the Galapagos. There were no biologists on that cruise because at the time, it was inconceivable that there could be life at the bottom of the ocean because it was thought that there could be no energy sources. Now, a year before that discovery, Viking landed on Mars. So the only life detection mission to land on the surface of Mars was designed and sent to the surface before we even knew that we could have life on the subsurface of Earth. So it tested for very specific types of life, the types of life that we have here on Earth's surface that eat organic carbon compounds and utilize organic molecules or use things like oxygen and CO2 in their metabolism. So while this was a brilliant set of experiments, It was very, very limited in its capacity to actually detect and understand microbes that live in extreme environments. And these are the environments that we now think microbes on Mars, if there still are microbes on Mars, might exist in. So as scientists, we like to take a natural system and break it down into its component parts. And so we like to take a very complex living system like a cell and break it down into what makes it a cell. So why is a cell a cell? Well, it can metabolize, it can reproduce, it takes in energy, it can grow, it evolves, it has DNA. But when we break apart these complex systems, we really lose track of their emergent function. So if we were to never see a tree branch and only ever see the needles and branches lined up like we see it on the right, we wouldn't have a very good idea of how that tree branch looks or functions. Similarly, I'm sure there are a number of talented astronomers in this group. If you never saw the stars in the night sky as they exist and only ever saw them categorized by maybe brightness or distance from Earth, we'd never understand how they formed. We'd lose track of this emergent function. We'd lose track of the nature of the universe. Similarly, when we only look at the parts of life that make life, we lose track of the emergent property of life itself. So how can we search for life without looking just at its component parts? Because in order to look for its component parts, we need to know what they are. And we've already kind of talked about this idea that we have this terrestrial bias. We only have life on Earth to look at. And so how do we know we're not still basically sending out more and more and more Viking level experiments to the surface of Mars? Because we have such a limited understanding of the possibilities of life. So this is just one of my favorite science quotes. Chaos was the law of nature, and order was the dream of man. So I want to take back this idea of this microbe. So we actually, my colleague, Dr. Alexander Pontefract, and I took this image, and we called him Scary Harry. And so Scary Harry here is wired into the rock. And we talked about all life needing energy to grow, and that this microbe is actually gaining its energy by transferring electrons to the rock. When it does that, it changes the rock in some way. And those changes that are only due to a life process are called biosignatures. And sometimes biosignatures are very, very, very easy to identify and to distinguish. For example, any child could tell you the difference between a nest and a pile of sticks. But what if we had a type of bird that didn't build perfectly round nests? Or maybe we had a huge storm come by and we're looking at something more like this. At some point, we can no longer clearly distinguish. So what is it that allows us to easily distinguish a bird's nest from a pile of sticks? What is it that makes a biosignature a biosignature? So we know that these are changes in the environment that are induced by a life process. But in order to detect them, we need to know what they are. So we're going to run a little bit of an experiment here just to demonstrate how important it is to recognize our terrestrial bias and the near infinite possibilities there might be out there for other types and forms of life. So I'm going to send everybody on a bit of a mission. I want you to imagine that you're in a grocery store or you're on Instacart, and I'm giving you a list of items, a list of those characteristics that describe one item. And I need you to go into that grocery store and find that one item that I'm describing. So we have flour, sugar, eggs, milk, and zucchini. So what is it that I want you to go and get? What am I describing with those attributes that's sitting in the grocery store? So go ahead, type your answers into the chat, and let's see what everybody comes up with. Don't be shy, anything goes.
We have one guess of zucchini bread.
Okay. I've heard things like quiche or an omelet, zucchini bread, zucchini muffins. So there's a number of different things that this list could be. But in this case, I'm thinking of something very, very specific. Any last minute guesses out there? Actually describing chocolate cake. You're probably thinking, how does this list, this is not the best list to use to describe chocolate cake. And there are a number of things wrong with this list, right? We have an incomplete list. Obviously, I'm missing chocolate. And there's a very specific, very atypical ingredient. I mean, I like to put shredded zucchini into chocolate cakes because it keeps it quite moist. We're also missing the process, the time, and the instructions. So we're missing the baking, the mixing, how much of each one of these things. And this is similar to our terrestrial bias. We have life on Earth. Maybe the attributes of life on Earth are relatively incomplete. Maybe Earth is really hyper-specific and all life elsewhere in the universe has chocolate in it. Or maybe life on Earth is really, really weird. Maybe only life on Earth has zucchini, but all life on Earth has zucchini, so we think that all life must have it. And of course, we're missing all sorts of things with just that list of attributes, right? We're missing that emergent structure. We're missing the lifeness of what makes life life. And so these are all things that illustrate this terrestrial bias. We have a data point of 1, the Earth. So this gives us kind of 2 options. So do we find life as we don't know it? So this is kind of known this as the second genesis of life, or life 2.0, after Dr. Chris McKay, and this applies that life might be quite common in the universe. It requires identifying traits universal to life. So this requires identifying things that all life in the universe must have for it to be life, also called agnostic biosignatures. So an agnostic biosignature is a universal trait of life. Now, this is really difficult to come up with because we only have this hyper-specific subset of life as we know it here on Earth. But let's take an example of amino acids. So all life on Earth uses amino acids, and these amino acids make the proteins. And proteins are what make life structurally look like life. Proteins make us look like people. Different proteins might make a cell look like a cell. And so proteins are really these structural units that help life function. Now, there are thousands and thousands and thousands of possible amino acids, but life really only uses a subset of them. And it uses a subset that also contains some very, very complex amino acids. So we have this complexity, we have this selectivity, and then life is also patchy. Life isn't distributed equally, everywhere. And we know this just because of habitable zones, right? Life isn't distributed equally over the entire solar system. Life can only exist within the habitable zone. It can only exist within our concert halls, where we'd expect life to be, where it would be habitable. So we have this idea of complexity, selectivity, and distribution. So I'm going to actually talk about 3 really specific complex amino acids a little bit later in the talk. So the tryptophan, tyrosine, and phenylalanine are 3 complex amino acids that all life on Earth uses. Just a little philosophy question. Is an agnostic biosignature itself an oxymoron? So is life as we know it here on Earth completely separate from unfamiliar life, meaning there's no such thing as a universal life trait? Or is life as we know it just a small part of all of the possibilities of life out in the universe? Now, another agnostic trait of life that we believe is that all life needs energy, whether it's life on the surface, whether it's life in the deep subsurface, or whether it's life, on very primitive Earth, or life on Earth today. Life needs energy to carry out life processes, such as growth or evolution or reproduction. So life is a prerequisite for life. So the next few slides here are modified from Professor and Dr. Terry Holler at NASA Ames. So there's kind of two reports here. These are just examples of just how important this idea of energy is to life. So this was the National Research Council's report on the limits of organic life in planetary systems. And it was stated in this report that the requirement for thermodynamic disequilibrium, also known as available energy, is so deeply rooted in our understanding of physics and chemistry that it is not disputable as a requirement for life. All other criteria are not absolute. So basically, this big report came out and said the only thing that's an absolute requirement for life is energy. In a very famous essay by Schrodinger called "What is Life?", the living organism can only keep alive by continually drawing from its environment negative entropy. Negative entropy is also just another physics term for available energy. So energy is required for life. When we think about the distribution of energy available for life on Earth, the first thing we think about is that photosynthetic energy, or light captured from the sun. And indeed, this is the most energetic. So this is where the most energy that is available for life to use. So we have 173,000 terawatts is kind of the global irradiance. And now photosynthesis is not a particularly efficient capture. It's probably one of the most efficient that we have, but it only captures about 780 to 2,300 terawatts. And then the life that can actually be transferred into chemical energy from that for life is down to about 63 to 105 terawatts. So all surface life on Earth is dependent on organic photosynthate. So basically, all surface life, all life on the surface of Earth, including us, is somehow dependent on some other form of life that's captured energy from the sun. So without energy from the sun, there would be no surface life on Earth as we know it. Now, what about in the subsurface? What about where we don't have energy from the sun and we don't have that kind of filtering down of that organic photosynthate? So we can get energy from the Earth. And so this is based on a series of calculations as well. So we have different types of reductants, or different types of elements that can actually grab onto electrons, just like we pass electrons on to oxygen, which is one of those processes in photosynthesis that occurs. Now, these energy fluxes are in gigawatts. So orders of magnitude smaller, much, much smaller than the energy available for photosynthesis from the sun. So in the absence of photosynthesis, life can use geochemical energy. But just notice how much smaller in magnitude the energy available is. So this means that the amount of biomass that could be supported in this energy regime is smaller. And it also means that how quickly that energy is used by life is takes a much longer time. So we have slow growing life systems that can't grow to a very big or giant state like we have on the surface. So just to put that into context, our power output, we are about equivalent to a light bulb. So we're all light bulbs. And then you can see up at the top is the global photosynthetic energy capture. And there we have two different types of geochemical energy. So both in terms of if the ocean has oxygen in it, or if the ocean doesn't have oxygen in it. So this is kind of the energy scale, or the available energy that constrains biomass, so the amount of life that can be present, and growth rate, how fast that life can grow. And there are variations across orders of magnitude. So really, when we're searching for life, we have this regime of follow the energy, because that is the only absolute requirement for life. So how do we do that? So I'm going to just talk through this diagram really quickly here. So I'm going to start on the right-hand side. Life needs energy. I've just denoted energy here by delta G. And here's my favorite definition for life. Life is nothing more than an electron looking for a place to land. So that's called energy transduction. So basically, life can take an electron, drop it onto another molecule, it gains energy in that process, it uses that energy to build more life. Where we have lots of energy on the surface, so kind of at the top of this funnel, we have the ability for life to grow really massive and really quickly. So it can create a biosignature that's very obvious. It's very far apart from the abiotic signal. But as that energy regime gets tighter and tighter and tighter, so as the available energy becomes less and less and less and less, the biomass becomes smaller and the growth rate becomes slower, and the potential for that life to produce a very obvious biosignature becomes lower and lower and lower until that biotic signal is pressed up right against that abiotic signal. So in these really slow energy regimes, it can be very, very difficult to actually differentiate or identify biosignatures. And this is the energy regime that we're working in the deep subsurface of Earth, but also the energy regime that we're working in when we're searching for life on Mars. And this is why we can learn so much about searching for life on other planets by looking at for life deep in the Earth's subsurface. So where does life exist in the Earth's subsurface? There's a whole bunch of different environments. It can be under ice sheets, under glaciers. It can be deep in the ocean sediments, near hydrothermal ridges, fractured crust around impact craters, in between sand grains in a hyper-arid desert. So there are all sorts of places in the Earth's surface where life can exist and gain energy from these geochemical reactions. So I did a lot of work at the Sanford Underground Research Facility in Leeds, South Dakota. And so this is also known as the Deep Mine Microbial Observatory, or the DEMO network, that was actually set up by Dr. Maggie Osborne, who's now at Northwestern University. Facebook reminded me that on this day, back in 2018, I was actually 5,000 feet underground looking for life. So doing exactly this on this day. So when we get to the Sanford Underground Research Facility, we often go down about 4,500 feet down a shaft. We get to one of these drifts. We hop in a minecart. And so right now we're going through Paleoproterozoic ancient ocean crust, 5,000 feet underground. And so basically this is an ancient back arc basin or an ancient ocean floor. And there are water systems or aquifers, deep subsurface fluids. And in those fluids, there's life. And the life is actually using chemicals and energy within those fluids to grow. Here's just a couple of snapshots of what it looks like down there. On some levels, we're lucky enough to actually have some chemical toilets. You can see somebody with a sense of humor put up a for rent sign. So that is a very, very luxurious deep sea drift. And here we are at one of our sites. And so this is almost 5,000 feet underground. There's no electricity, no light down here. It's about 40 degrees Celsius, about 100% humidity. And what I'm doing is I'm hooking up all of these filters to capture life into what's known as a deep aquifer. And you can see that white pipe jetting out there underneath me, and that's the pipe that feeds into that deep subsurface aquifer. And we allow these cartridges to sit for about 3 months so that we can grow biofilm, so we can culture the microbes that were in this deep fluid. And after 3 months, we take them up, we bring them up to the surface, and in the surface, we can actually then try to visualize them. Now, remember those 3 molecules I mentioned, those 3 amino acids, tryptophan, tyrosine, and phenylalanine. Those amino acids are particularly important because they give us a very good signal with a very specific technique called fluorescence spectroscopy. And so what you see here on the left is a map of the fluorescence of tryptophan. And remember that tryptophan is a very complex biomolecule that we think all life on Earth uses. And so by mapping tryptophan, we actually use that as a proxy for mapping the microbes on the surface. And if you take a look at one of those bright green pixels there on the right, this is a scanning electron microscope image of the cells that were in that spot. And so it's the tryptophan in those cells that are fluorescing that we can see using our deep UV spectroscopy. And so what this technique is we basically have a laser light going in. That laser light interacts with a molecule like tryptophan, and then laser light comes back out. So there's a couple of different types of light that can come back out. I like to think of spectroscopy as basically light goes in, light comes out. And working with the SHERLOC team is looking at two really specific types of light that come back out. Fluorescence, which is most of the light, and what's called Raman scattering. So Raman photons or Raman light is basically light that's been changed in energy in some way. So the laser light interacts with the molecule. That interaction kind of absorbs some of that energy, and then the light that comes out is shifted in energy from the original light that goes in. And that shift is called the Raman shift, and it's really specific to the interaction of the molecule. So we can actually use that Raman shift to fingerprint organic molecules. And this is the technique that's used by the SHERLOC instrument on the Perseverance Rover to look for organic molecules as potential signs for life on Mars. So this is the Perseverance Rover as it looked when I was working with the SHERLOC science team. So this is the Perseverance Rover in the CLEAN lab at NASA JPL, July 18th, 2019. Here's a slide just showing the SHERLOC instrument. So the SHERLOC instrument is that big club-like thing on the articulated arm, and it uses deep UV fluorescence and Raman to actually look for organic molecules the same way I was looking for them in the deep subsurface. Now, this is the lab version of SHERLOC that I worked on at JPL. So this was the version where we did all of the experiments before the engineering team packaged it up very nicely into that flight instrument. So this lab version is called MOBIUS. And MOBIUS stands for Mineralogy and Organic-Based Investigations with UV Spectroscopy. NASA's famous for its very convoluted acronyms. But basically, we have our deep UV laser source. We have our objective where the sample sits, the spectrometer that actually takes in that signal, and then our liquid nitrogen cooled CCD detector. And for people that are really interested in the photon flow and light flow, here's just the instrument setup. We have our objective, we have our spectrometer, and a number of different mirrors and lenses. So we have an LED light ring. The LED light ring goes down to the first set of mirrors, through an adjustable mirror, through the imaging lens into our context camera, so we can actually take a picture of our sample. We then use the laser to fire a laser pulse. It hits a grating, goes up to a secondary mirror, through that injection filter, back through the objective, down into our sample. So it hits our sample, and when it hits that sample, it interacts with the sample, and it generates that Raman shifted photon. So that Raman shifted photon then comes back through the mirror, through the injection filter, straight into our spectrometer. So it hits a couple of different gratings on our spectrometer before going into our detector, where we see the Raman spectrum that can be used as a fingerprint to actually identify the molecule that we see in the sample. So what does a cell look like to a deep UV Raman instrument? So these are two pictures of what a cell looks like chemically. The picture on the left are all of the components of a cell. The picture on the right is what a deep UV Raman instrument sees. So deep UV Raman instrument is only sensitive to a selection of the biomolecules within a cell. So even though a cell is a very complex system, by using deep UV Raman, we can simplify that system to really only look at what are called the Raman active components. The problem with those Raman active components, none of those are unique biosignatures. Every single one of those components can also be formed through abiotic processes. They're found in meteorites, they're found in carbonaceous chondrites. They can also be formed in hydrothermal vents at the bottom of the ocean. So while life contains all of these components, none of these components are specific to life. So if we detect them, how do we know that we're actually seeing a cell when all the Raman instrument can see are these specific molecules? So this is one of the research projects that I was involved in at JPL, where with some colleagues and I, we decided to break down all of those components. So first, what I'm going to show you is on the left-hand side, we see a black spectrum up at the top. That's what an E. coli cell looks like to a DUV Raman instrument. Now on the right-hand side, we've taken all of those really specific components. So we've taken our tyrosine, our tryptophan, and our phenylalanine on the top, and then we've taken the nucleobases. And so these are the components of DNA. And I'm just going to talk about two of them here, adenine and guanine. Now, these bases can exist just as a nucleobase, and so those are that first molecule. They can exist as a nucleotide, which is a slightly more complex molecule, and then they can exist as a piece in our DNA. So they can be all of those nucleotides attached together to form a DNA fragment. Now, as that molecular complexity increases, the chance that that molecule formed in the absence of life decreases. So as far as we know, DNA can only be formed by life processes. We're a nucleobase. Nucleobase can be formed by many different processes. It doesn't need life. DNA needs life. So the Raman instrument really only sees the nucleobase. So it's sensitive to the nucleobase in the DNA structure. And what question I was asking is, can we tell the difference between just the base and the base in DNA? And it turns out we can. And so with this increasing structural complexity, we have really simple structures that are consistent with abiotic systems that don't need life. And we have really complex structures like a nucleotide, the precursor to DNA, that are unique to biological systems. And we found, we have that black line in both pictures, that's that baseline of a cell. If we took just the simple structures, just the nucleobases, it didn't matter how we recombine them, we could never get back to the spectrum of the cell. And that's that pink line. So if we combine all of those components in their simple form, we never get back to the cell. However, if we take their more complex form, that nucleotide, we get very, very close to the cellular spectrum. So we were able to demonstrate molecular complexity as a threshold for life detection. So even though this Raman instrument on Perseverance is only sensitive to identifying the nucleobase, with improvements in that technology, it can actually be used to extract the molecular complexity around that molecule, which can actually give us some type of assessment on how likely it is that that molecule came from a living system. And so that's really getting back to this idea. If we just look at those simple components there on the right-hand side, we miss the complexity of the living system. But we've been able to show that by looking at the system as a whole, we can actually extract that molecular complexity. So we're no longer interested in very specific components. We just want an idea of how complex those molecules are. And the complexity of those molecules actually tells us more about whether they're from life or not, rather than the absolute identification. And that goes back to this idea of a terrestrial bias. There could be life out in the universe somewhere that doesn't use the amino acids that we use. So the exact detection of those specific amino acids isn't as important as how complex they are, because we think that all life in the universe, because it uses that energy, and it uses that energy to continue to build up complexity, the complexity of those organic molecules is what's important. And so in a very real sense, the whole is more than the sum of its parts, especially when we start looking for life beyond Earth. So yes, we're looking for signs of life on Mars, but when we're looking for biosignatures, what we're really asking is what constitutes life. I'd like to finish by acknowledging all of the people that I've worked with. I mean, none of this work can be done in a vacuum. And so there are people that I've worked with at York, at Caltech, NASA JPL, University of Southern California, the Northwestern team, the Bigelow team, the people that came with me into the field, the people at Sanford Underground Research Facility down underground, the NASA Astrobiology Institute underground team, and then some of my longtime collaborators, Gordon Azinski, Alexander Pontefract, and Charles Cattell. So love to open up to any questions.
Thank you very much, Dr. Sapers. This has been a wonderful talk, from sort of the sounds of silence and nucleotide cakes all the way to microbes on Mars. I have to say the search for life sure does seem like it's a very interesting one. Now I'm sure we have some questions, so I'm going to go ahead and send you over to Emma for questions from YouTube. Take it away, Emma.
Hi, okay. This first question comes in from Eric Briggs, who wants to know, can you tell us a little about the phosphine finding on Venus as a biomarker?
Yes. And so remember how I said that there's absolutely no definitive biosignature. There's no smoking gun, unfortunately. Unless it's waving to us or it's highly complex like a fossilized dinosaur skeleton, there's always going to be skepticism. And so the phosphine finding is one of those things that's very, very interesting. It's one of those things that it can be difficult to explain that finding in isolation, and it is compatible with life. I don't think it's a smoking gun. I don't think it says, oh, there's life here. And I don't even think that those original papers were actually using it to say, this is an absolute sign of life. But could it be a biosignature? Sure, definitely. Do I think that the detection is real? I think that there is more and more mounting evidence that supports that detection, that it wasn't an artifact. I know that there's a lot of back and forth in the literature, and that particular remote spectroscopy is not my strong suit. So I'm sure there are people in the audience here that know more about that spectroscopy technique in detail. But my understanding of reviewing all of the literature around it is I believe the detection. And I think it's an interesting detection. And as we learn more and more about the environment and get other lines of evidence, we can start building up this story to support whether or not it's a biosignature. So I know that's not a simple answer, but unfortunately there are very few smoking guns in the field of astrobiology.
Well, that's still very cool. Ron McNaughton would like to know, can the existing Raman equipment on Mars be modified to make it more sensitive?
So as it stands on Mars, that equipment in situ on the rover cannot be modified. That technology and technique can be modified. And so I think if we're sending other generations of rovers, and I think that the next kind of lander on Mars that was mentioned in the most recent decadal survey was the Mars Life Explorer. Now the payload and instruments for that particular mission have not even started to be discussed. I think there's a nominal set of instruments that are kind of identified in the proposal. But no, for sure, future iterations of a DUV Raman instrument with changes in grading, changes in optics, and refinements in calibration could be made more sensitive.
Well, great. Thank you very much. That's all the questions we got tonight.
Excellent. Well, thank you again. Thank you very much for having me. Please feel free to reach out if you have any further questions or comments.
All right. Well, thank you very much once again, Dr. Sapers. We could certainly stay here talking quite a while, I think, about Mars and how to look for signs of life in the solar system. But we do have to wrap up for tonight. And with that and all of this great excitement, I'm going to go ahead and hand over to our president of Toronto Centre RASC, Tom Luton, to finish off the evening. Over to you, Tom.
All right. Well, thank you very much, Elena, and thank you very much to our wonderful speaker. Very interesting talk. So, good evening, everybody. Let's get started with the announcements. So, first of all, this is very recent news that has been a lot of people asking questions. As you may have heard, the province of Ontario has plans to move the Ontario Science Centre down to Ontario Place. And a lot of people have been asking, what does this mean for the Toronto Centre? We've been in contact with the Science Center, and they've actually reached out to us, and they wanted to let us know a couple of things. Direct quote from the email: "We want you to know that we greatly value the relationship between the OSC and Rask Toronto Centre and are committed to continuing our work together. For over 50 years, the Ontario Science Centre has ignited a passion for science in millions of children, families, students, and teachers, and we haven't done that alone. Your partnership has been and will continue to be critical to this work. Programs and events will continue in our current location, but also at Ontario Place. Construction is expected to begin in 2025, with an opening slated for 2028. So, in the short term, we're not going anywhere. We're still going to be having our meetings at the Science Center at Don Mills and Eglinton. Um, and it's going to be that way for at least a couple of years. Um, And as we know about provincial and other government projects, construction often gets a little extended past the deadlines. So, what our longer term future is and what things are going to happen, um, we will wait and see. But for the short term, for the time being, nothing has changed. We are still at the Science Center. So, and so moving on to our more usual announcements, I'd like to welcome everyone. I'd like to say thank you to everyone who's joined us. We've got two types of meetings, both online and in person. We have a recreational astronomy nights, which are both online and in person at the Science Center, and we have our speaker nights, one of which you've just seen, which are purely online. If you're watching us, joining us live on YouTube, please say hello. Enter some questions for the presenters as others have done so. If you're a new member, please introduce yourself. And you're coming to us from far outside the Toronto area, please let us know where you're coming from. So our next recreational astronomy night is on Wednesday, the 3rd of May, 7:30 p.m. Like I said, in person at the Science Center and online. Andy Beaton will be discussing the sky this month. Clay Davies will be talking about telescope mirror making, a superb polish with a cheap but vile, slow, messy slurry. And John Percy will be discussing the mysterious long secondary periods in red giants. Explained or not? Um, you can join us live on YouTube. And if you've got something you'd like to present, please drop a line to Paul Markov, our Master of Ceremonies. Our next speakers night is on the 17th of May, 7:30, live on YouTube. Connor W. Hayes, who's a Ph.D. candidate at York University, will be discussing Water, Water Everywhere, a history of the hunt for lunar water from Harold Urey to Artemis and beyond. Like I said, online live on YouTube. Coming up in the next few weeks, our first of our springtime City Star parties is going to be at Bayview Village Park on the first clear night of the week of April 24th to 27th, 8 p.m. to 11 p.m. Dark Sky Star parties details still to be determined. Coming up at the DDO, we have our astronomy speakers night on April 29th at 9 p.m. in person. Dr. Keir Rogers, A Search for Dark Matter in the Cosmic Web. You have to register online for this event. Links can be found at raskio.ca. DDO Planetarium Day is April 30th with two sessions, one running from 1 p.m. to 2:30 p.m. and the second running 2:30 p.m. to 4 p.m. Also in person. And again, you have to register online with the links at raskto.ca. Also, that weekend is our first of the seasons of Millennium Square public stargazing event. Friday, April 28th from 6 p.m. to 11 p.m. Join us and our sponsor, Durham Skies, for an evening of free public stargazing along the North Shore of Lake Ontario at Millennium Square. Observe the moon and stars through our telescopes, check out the literature at our booth, and ask us some questions to learn more about the stars and the planets. You can bring along your own telescope. We'll be happy to help you set it up and aim it at the moon. Reminder that the temperatures down by the lake are colder than what you'd find more further inland. We're still recommending that you wear masks and to use some hand disinfectant before handling all the stuff at our info booth. And please check our website for a go no go decision based on the weather before heading to the square. Oh, and this also applies to the previously mentioned um, city star parties. Coming up on the 29th of April is Astronomy Day at the Ontario Science Centre. From 10 a.m. to 12 p.m., there'll be solar observing at the telescape as well. We're hoping to have a RASC info table. There are also going to be three presentations at the Science Centre that afternoon. Frank Dempsey will be discussing Indigenous legends of the constellations at noon. Dr. Mark Tovey will be showing artifacts from the Cronin Observatory at 2 p.m. And then Frank will be giving a second talk, topic to be announced at 3 p.m. Tickets are available for the 2023 RASC General Assembly on sale. The event is May 5th to 7th. Full details at the website rascga2023.ca. So, the good news is the road to the CAO, the Car Astronomical Observatory, has reopened. We hoped it would be in April, and it was in April. So, access to the CAO facilities are by members and families only in a modified communal fashion with a total occupancy limited to 5 individuals. The upstairs bedroom is only for upstairs bookings. Max occupancy for is 2 people from the same family per bedroom for a total of 6. Communal residents 3 people. Mask wear for making your bookings. Our jobs board. We're looking for a new treasurer. Adrian Aberdeen has been working incredibly hard for the last several years, but he needs to step back. And so we're looking for someone with an accounting background or a financial background who can be our new treasurer. This is a high level job. This is very, very important. So if you'd please roll, if you have those skills, please drop me a line. We're also looking for an education and public outreach chair, a light pollution committee chair, and a volunteer committee chair, as well as we'd like to get a marketing committee off the ground. We're always looking for education public outreach committee members, especially people who can present online and who can operate telescope cameras for virtual star parties. A reminder that to volunteer, you must first be a member. Please drop me a line at president@rascto.ca. This is the point where I get to plug the benefits of RASC membership. You can renew and sign up online at secure.rasc.ca. Gift memberships are also available from the national office at mempub@rasc.ca. In addition to access to all of the events and access to the CAO as a member, you receive also our Observer's Handbook and copies of the RASC Journal. And with that, I'd like to wish you all a very pleasant evening. I'd like to thank you all for joining us. Please follow us on all the forms of social media that we've got listed here. If you've been watching us live on YouTube and you like what you've seen, please like and subscribe and hit the notification bell. Stay safe and keep looking up. Good night, everybody.